So continuing ahead with the errors in hypothesis testing and the impact of selecting the confidence level or alpha of the test, uh, we are going to conduct a few thought experiments and figure out what does it mean when an error happens on different kinds of tests. For example, what is more harmful when we are conducting a pregnancy test, a false positive or a false negative? So in this example, we're going to start off with the null and the alternative hypothesis. So whenever we do a pregnancy test, what should be the null and what should be the alternative hypothesis? For example, in a pregnancy test, we start off with the assumption that the person is not pregnant, and then the test confirms whether the person is not pregnant or pregnant. So what is more likely to cause an error? What would be a type 1 error in this case, and what would be a type 2 error in this case? So let's start off. Let's say example is pregnancy test. H naught being not pregnant and alternative being pregnant. So should we have a low alpha or a high alpha over here? So should we go with a low alpha or high alpha? And remember, alpha is also the probability of me committing a type 1 error. So which error is more likely to be harmful? Telling a pregnant person you're not pregnant, or a not pregnant person that you're pregnant. So the type 1 and type 2 errors that we're going to have the error of the first kind. So the error of the first kind, as we've mentioned before over here, is rejecting the null when null is true. So rejecting the null which is not pregnant. So telling a person pregnant when not. And what is the second type of error? The second type of error is accepting the null when null is false, saying not pregnant when actually pregnant. So in this case, which error is more likely to cause harm and why? So I think it is quite evident that if we tell a person who is actually pregnant that the test has come not pregnant, this can have serious repercussions. Why? Well, there is obviously the health aspect. A person has to change their lifestyle, the eating habits, drinking, if any, medication, etc., tests, further tests, doctor's appointments. These are all the series of actions that need to be taken when a person is pregnant. But when the test comes out not pregnant, the person never knows about it until much later. So this kind of error can cause serious repercussions. But if I tell a person who is actually not pregnant that they are pregnant, what do? They always follow with a doctor's appointment. A doctor will go ahead and tell them, you know what, a mistake has been made, you're actually not pregnant. So no harm, no foul. Right? In this case, the cost of a type 1 error is low as compared to a type 2 error. So a type 2 error can cause more harm than a type 1 error. So we have to minimize type 2, and we have to and we can. So I'm not saying that type 1 can be ignored, but what if given the parameters of a test, a type 2 error is more serious than a type 1 error. So we may want to minimize type 2 at the cost of type 1. So in this case, the question again is arising, should we go for a low alpha or a high alpha? So how do we resolve this? So if we may want to draw it out. So if we want to go with a low alpha, so I'm just going to open up another sheet on MS Paint and remind you how does it work. So let's say I have a distribution over here, and this is the normal distribution around there. Let me make it a little better. Yeah. So this is my null hypothesis, or this is the hypothesized mean. This is the hypothesized mean. When I have a high alpha, that means my rejection region is large. I have larger rejection regions, and this is my acceptance region. So I am less likely, with large alphas, I am more likely to reject. But if I have a low alpha, therefore my rejection region goes even smaller. So I am going to accept more. So with a low alpha, I am more likely to, so low alpha, more likely to accept. And what is my null hypothesis? The null hypothesis is not pregnant. So this is the not pregnant region and this is the pregnant region. So rejection tells me that the person is pregnant and acceptance of the null hypothesis I'm not pregnant. So which error is more likely to cause a problem? When I do commit a type 1 error, when I say, sorry, when I commit a type 2 error, when I say not pregnant, when actually pregnant. So when does not pregnant happen? So not pregnant happens in the acceptance region. So I have to minimize the acceptance region and I have to maximize the rejection region which says a person is pregnant. So if I go with a large alpha, I am more likely to reject the null hypothesis that the lady is not pregnant. Therefore, I am less likely to commit a type 2 error, but I am more likely to commit a type 1 error. A type 1 error is saying the person is pregnant when actually not pregnant. And we have already discussed the fact that a type 1 error is less serious than a type 2 error. So in this case, a large alpha might actually help me. So that means I have but the test should be very, very sensitive towards pregnancy such that sometimes, and I say this with caution, sometimes not pregnant also comes out to be a pregnant, but it in no case should a pregnant person come out as not pregnant. And this can be avoided by having large alphas or small confidence intervals around the mean. So this is an example where I'm controlling type 1 and type 2 errors by selecting an alpha specifically designed for a pregnancy test. So let's move on to the next example where I'm going to do a disease test. It could be an AIDS test, it could be an Ebola test, it could be any kind of a bird flu or swine flu test. So again, in this case, let's think about it. What's more harmful, a type 1 error or a type 2 error? So let's start off with the null and alternative in this kind of a test as well. So whenever we're doing a disease testing, what is our null and what is our alternative? So our null is that disease is not present. So we start off with the assumption that when we draw the blood and we do a test, that there is no disease, and we are going to test for antibodies of a particular virus or particular disease. And if those antibodies are in fact present in the blood sample, then we go with the other hypothesis that the disease is present, right? So what is a type 1 error over here? So type 1 error over here again is going to be that rejecting the null when null is true. So saying person is ill, person is ill when actually healthy, right? What's a type 2 error over here? Accepting the null when null is false, null being disease is not present, saying person is well when actually sick. So what kind of error is more serious over here? A type 1 error or a type 2 error? What will happen if I commit a type 1 error? If I commit a type 1 error, a healthy person walks in, I do a test and I say, dude, you're ill, you've got the Ebola virus and you might die. Here, take a few drugs here, lie down immediately, put on a saline solution and whatnot. And what will happen over here? Some side effects, I'm sure, of the drugs, etc. Person may actually be mentally very disturbed, etc. But on the whole, it's an error has happened, but it's not as serious. What happens when I commit a type 2 error? A sick person who's actually has the Ebola virus walks in, we do a test, and we say, hey, all's well, go home. So not only will this person fall sick, the person might die. This person might also go on and infect few healthy people, which might have been prevented if I had tested positively or we had tested correctly. So in this case also, a type 2 error is potentially potentially fatal in this case, right? A type 1 error is unfortunate but not fatal. So it's an unfortunate error, type 1, that telling a healthy person that you are sick, but telling a sick person that you are healthy is can be potentially fatal. So in this case, what should I do? What kind of alpha will I go with? So assuming again that we are the null being that the person is healthy, and I have a distribution around the null hypothesis regarding the presence of antibodies, right? So this is the distribution. So I have, sorry, I have the mean, correctly, yeah, and I have the acceptance region around this. So the acceptance region is the region, so this is the acceptance region which says the person is healthy. The rejection region tells me the person is sick. So should I have a large acceptance region, or should I have a large rejection region? So if I have a large acceptance region, if this region is large, right, and this region is small, then I'm more likely to in fact accept the null when the null is false, i.e. more likely to say healthy when not. So what happens if I reject, if I start having a smaller acceptance region? So I reduce the acceptance region over here, therefore the rejection region now starts to increase over here. So in this case, I'm more likely to say sick when actually healthy. But my type 2 error goes down. So in this case also, having a large alpha, or alpha is the size of the rejection region, a large alpha is helpful. Large alpha is going to reduce type 2 errors. So in this case also, when we want to reduce a type 2 error, that the person is when saying that the person is well when they actually sick, I can go with a large alpha which has a larger, let's say, unwell region, and I am less likely to tell a sick person you're healthy, but on the conversely, I'm more likely to tell a healthy person you're sick. So type 1 error becomes big, but type 2 error is reduced by having large alpha over here. So in this case also, by controlling alpha, I am minimizing one kind of error at the cost of the other error, and I figured out which error is more important to minimize. So let's move on to the next example. A fire alarm is similar to a disease or a pregnancy test. So let's move on to more interesting, which is our legal system. For example, we are trying out a person accused of murder. So in this case, should we go with a large alpha or a small alpha? So let's start off with the assumptions again. What should be the assumption, or what should be the null when we are trying a person for a crime? So in most democracies, the H naught always starts off with person is innocent. So there's a well-known saying that in a democracy or in a mature legal system, a person is assumed to be innocent until proven guilty. So the onus of proving the guilt lies on the prosecutor. Till that point in time, the person is assumed to be innocent of the crime. So the null is that we are going to start off with the assumption person is innocent. Alternative, the opposite. Person is actually guilty of what we are assuming this to be, or whatever we are accusing the person of. So let's start off with the distribution again. So we have the distribution here, and we have the null hypothesis, the H naught, that the person is innocent, and we have the acceptance region here, and we have the rejection region here. So acceptance region is the probability of accepting the null. So this is the region where we are saying the person is innocent. This is the region that we are saying the person is guilty. So in case I have a small acceptance region, what will happen? If I have a small acceptance region, I'm likely to commit one kind of, so let's start off with what are the type of errors that can happen. So type 1 error over here. So type 1 error is, again I'll go back, I'll reiterate. Type 1 error is rejecting the null when null is true. Rejecting the null, saying a person is guilty. Guilty when innocent. So this is the type 1 error. What's the type 2 error? Rejecting the null, accepting the null when null is false. Accepting a person is innocent when guilty. So innocent when actually guilty. So what kind of error is going to be more catastrophic in this case? So in most legal systems, so now this depends on the legal system also, we are talking about democratic systems. In most democratic systems, we are okay to let a guilty person walk rather than convict an innocent person. So there's a very well known saying, it is better to let 100 guilty men walk rather than hang one innocent man. And that is what the assumption, and that's what the assumption we're going to apply on this case also. So the error which causes more harm to society is a type 1 error, holding a person guilty when the person was innocent. Since the assumption of innocence is on the person and it is up to the prosecution to prove guilty, right? We are already loading up the system to minimize a type 1 error. We don't want a type 1 error. So in this case, right, having a large alpha means that the guilty region is higher, right? In this case, a type 2 error is more likely to happen. So small alpha will give us larger acceptance region, right? Larger acceptance region. With a small alpha, let's say the alphas lie over here, I am more likely to accept the null than reject it. If I accept more null hypothesis or my acceptance region is large, I'm more likely to say a person is innocent when actually guilty, but less likely to say a guilty when the person is innocent. So in this case, small alphas is actually more helpful in minimizing a type 1 error. So unlike a disease test in which we go with large alphas, in a legal case, especially a criminal case, we might want to go with a small alpha. Obviously, if you are a dictator and you want to oppress and rule, in that case, you might rely on collective punishment. So you might want to hang a whole village just to ensure that you catch the guilty person or the guilty conspirators. So, but don't take me at my word. In a democracy, in a legal case, we want to go with small alphas.